for the Oxford vaccine group, and then specifically to talk a bit about COVID vaccine development, because we thought that would be of interest in Sheffield and Helton before. So the overview of what we do, what our group in the Department of Pediatrics in the university does, is all of these different things. So it includes vaccine development, but also training and teaching around vaccines, infectious diseases, both locally and internationally, and international research working both in South Asia and in Africa, and also since the pandemic here in Brazil, with an immunology laboratory as well, which is able to try and understand the development of immunity, particularly in early childhood. Now that Danielle is here, mucosal immunity, well, not here, but there, mucosal immunity, so that we can perhaps better understand how we might develop vaccines in the future and evaluate them. And today we have 15 principal investigators, you can see here, who cover a wide range of different skills, from statistics and bioinformatics to vaccine development, but some focusing on pandemics, others on routine childhood vaccines, but a wide range of different skills amongst the PIs in the team. And our portfolio of studies goes right from the sort of discovery, the initial innovation around vaccines, through preclinical development, manufacturing, all the way through clinical development. And I think an important point about this slide is that we don't have products that go all the way through for all of the different stages of development. But we have collaborations with biotechs and with industry, which we've done for decades at phase 2 and phase 3, so that within the team there is always a group of experienced people who are used to doing later phase clinical trials. So when we do have our own products, we don't have to then invent how to do those later phase studies. And similarly, several of us are very involved in policy, so we can focus on research that's going to be important and impactful later on in policy, whether that's the initial design of vaccines, no point in designing vaccines that no one's ever going to recommend, but also to answer critical questions about how vaccines should be used differently so they have an impact on policy. And as I say, I think having this whole spectrum of clinical development always on, always switched on, even if we don't have our own, but always there, means that you can continue to drive your own products through, but also work with others to make sure they move through more quickly. And just as an example, this is the UK immunisation programme, and every square there that's coloured in purple is one where we've contributed to the current policy in the UK for those vaccines because of the research that we've done. And you can see that it's almost all of the blocks there, because over 30 years, nearly everything that's used in the UK has had some element of it, sometimes the pivotal clinical trials, but some element of it has been worked on by the team. So when I arrived in Oxford 23 years ago, that's what I looked like. And unfortunately, those 23 years and all these vaccines have actually changed how I look considerably. So it doesn't necessarily mean that the world stands still. Really importantly is the global network, because for some diseases they're much more common in different settings, but also if you are really interested in impact, where I live in a high-income country, we have much less impact with vaccine development than you do if you're driving development in settings where there's a much higher burden of disease. And I'll show you some examples of that in a moment. But we're very fortunate to have collaborators in many countries who we can work with to try and drive the development forwards. And so just to give a few examples, this is some work on the differences between B-cell responses to polysaccharide and protein polysaccharide conjugate vaccines, showing differences on this slide in memory responses, but also in trying to characterize the development of B-cell immunity in infants, and the requirement for numbers of doses in infants to induce strong immune responses, and how those then determine whether you have persistence of antibody and memory responses. And I don't have time to go into this in detail, but here's some of the PhD students who worked on this over the years. But one of the critical points here about looking at the schedules of vaccines already being used and how they might be used better in order to have persistent protection were these studies which we did, which were started just as serological studies, showing that after infant vaccination with these meningococcal vaccines, that immunity disappeared very rapidly during childhood. And so we saw that there was no longer any protection, because vaccinating early in infancy doesn't induce persistent protective antibody. And because of this disease being very rapidly fatal, the memory response, so relying on immunological memory, is insufficient to protect children. And so with this studies, we were able to show that if you gave doses to teenagers rather than to babies, that you get much more persistent antibody. And because teenagers and young adults carry this organism and actually are the ones responsible for transmitting it to the whole population, if you protect teenagers, you don't actually need to vaccinate young children who are the ones who actually have the highest risk of disease, because once you've blocked transmission, you don't need to vaccinate other people in the population. And so these were critical policy questions, a licensed product, but using the ability to get out into the community, take samples, and trying to understand the epidemiology, and then run vaccine trials to show that you can actually induce this. And that's now become policy in many countries that use these vaccines for teenagers. Do you use the meningococcal vaccine in teenagers? I think in Chile they do in teenagers, but not in teenagers. The group B meningococcus was a bit of a bacterial vaccines theme as this first part, so we're most interested in bacteria, Daniela and I are. There's others who like viruses, but so this was the Men-B vaccine, the group B meningococcal vaccine being developed at the time by Novartis, who were then bought by GSK, so it's now GSK's vaccine. And the first ever trial in babies was run by our team in Oxford, and then we led the pivotal phase 3 trial across Europe for this vaccine, which led to its licensure, and had great headlines that appeared like this. Of course, unfortunately, this isn't quite true, but it certainly inspired the team to keep on working on these vaccines. And moving to thinking about the global question, so as I'm sure you'll know, globally the highest or the greatest cause of death in children under 5 years of age remains pneumonia. And pneumococcal vaccines have been available now since 2000, so 24 years, and yet many countries were not using them. And so exactly 20 years ago now, we started studying pneumonia in children in South Asia, which is where, as you can see on here, the red dots are deaths. So the highest proportion of deaths in the world were happening in South Asia. And the country that we have been working in over that 20-year period is Nepal. This is the hospital in the south of Kathmandu that we've been working in. First of all, just simple clinical observation on the rates of pneumonia, what the causes of pneumonia were in children. And then working with the government, demonstrating that new vaccines which were available at that time were highly immunogenic in children and had an impact on, again, carriage of these bacteria in the upper airway. And so here you can see a child with severe pneumonia on the right hand. Image is an X-ray showing pneumonia on the right upper part of the lung. And this is a child, if you could be there, this child had very, very rapid breathing with the skin between the ribs being pulled in because the child was working so hard with a severe pneumonia caused by pneumococcus. And very sadly, this child died shortly after this photo was taken. And so it's just a real reminder just of these infections, particularly in settings where the poorly nourished children living in environments where there's a lot of air pollution, both indoor and outdoor air pollution, have a very high rate of this fatal disease. And so working with the government, we were able to demonstrate the vaccines made a good immune response. They could block colonization in the upper airway. and in 2015 the vaccine was introduced in the country, which this is the first dose being given in Nepal. And so being involved in those studies, we were then funded to show the impact of the vaccine, and we've been working on that over the last 9 years and have demonstrated considerable impact as a result of the programme with all the children in the country and vaccinated. So moving on very briefly on to the next disease that we've been focusing on in South Asia has been typhoid, and this is an infection spread in contaminated food and water, and we see very high rates of disease in many low middle income countries, and you can see most of the diseases centred here in the darker colours in South Asia, and we also find typhoid in many countries across Africa as well. And one of the real problems with typhoid has been the spread of antibiotic resistance, and this is just one particular clone of Salmonella typhi, which is called H58, and that has resistance to many of the antibiotics that would be routinely used in low middle income countries. And actually now in Pakistan, with the typhoid bacteria which are circulating are resistant to all conventional antibiotics, and for the clinicians in the audience it's only sensitive to carbapenems, but not to any of the other antibiotics that are available, cephalosporins and so on, which has created a real problem for being able to control typhoid in these settings. So we set out to first of all think about what information do you need in order to try and control typhoid. Well, first of all, you need to know a lot about the disease and what the burden is, because you can't persuade governments to introduce a vaccine unless they know that they've got a problem. It's going to be worth them spending the money on a vaccine later on. And so these studies were run in 3 different countries, Malawi, Nepal and Bangladesh. And in each of those countries, we had 100,000 people under surveillance, so a total of 300,000 people being monitored to look at the burden of disease in those populations. And you can see here on the top panel the number of children, or at least the incidence of childhood admissions to hospital with typhoid, to give some idea of the incidence in the population. And you can see that in Nepal, around 400 out of every 100,000 children were admitted every year in school-age children. In Bangladesh, it was about 600 out of every 100,000 were being admitted to hospital with typhoid every year. But the process of measuring the burden of disease is very imprecise, because some children, their parents can't afford to take them to a hospital, so they never get to test. And so you have to adjust for the behaviour that there is in the population. And just to give an example of just how difficult that is, in Nepal, where we looked in that population of 100,000 people and tried to work out what they were doing, we found there were 1,000 pharmacies in that population of 100,000 people, and most parents, just rather than spending money going to see the doctor, they went to the pharmacy and bought antibiotics, whatever the cause of the illness. And so most of the typhoid infections are actually treated by a pharmacist and not by the hospital. And so we would never know that they had typhoid. Secondly, that when you get into a hospital, in many settings, the doctors say, well, it's a very young child, we won't do a blood test because it's not very nice. And so you would then never find out that the child had typhoid, they just get given antibiotics. And then lastly, the sensitivity of the test is only about 50%, so if you do a blood culture for typhoid, you missed about half of the cases. So when you adjust for all of these things, you find that the rates that you could see here, and I can't point anymore, it's not working, but the rates went from around 400 per 100,000 up to thousands per 100,000. So high that no one's ever seen these rates before, and so we didn't believe them. So to try and prove this, we went into the community and took serial blood samples to look at seroconversion at a very large scale to find out what proportion of children were getting an infection that led to them developing a rise in antibody. And we found that these rates at the bottom here are right. You really do see this number of infections in the childhood population. And of course, for families who are very poor, going and buying antibiotics, managing the healthcare, particularly for the more severely ill ones, can plunge the whole family into an economic disaster. And we did some economic studies to show that huge impact. So this was an important disease. And the problem was that although there were some vaccines that were being developed, some new conjugate vaccines based on the polysaccharide capsule of typhoid, those vaccines had not moved forwards because there was a lesser well-known Indian company who was making it, and no one really trusted the vaccine. They didn't believe that it worked. And so we brought the vaccine to Oxford, and what we did was we got students, first of all we vaccinated people, and then we got students to, after they'd been vaccinated, to drink some bicarbonate contaminated with Salmonella typhi, the bacteria that cause typhoid, to see if they developed infection. And what we found in these studies was that in the control group, you can see here a high rate of infection, but in those who received the vaccine, we saw protection. So we were able to demonstrate that this vaccine protected using the challenge model, and made quite a lot of media interest because we had to pay the students to take part. And as you can see, I don't know what this would be translated into Brazilian reais, but it's quite a lot of money. So anyone who's interested in taking part in challenge studies in Oxford, please come. And the other great thing about doing these human challenge studies is you know exactly the point of infection, and you can follow them through that. So we were able to look at exactly which antibody responses were happening, look at functional antibody. We could also look at shedding in the stool, the feces of the bacteria, and they could demonstrate that the vaccine reduced the amount of shedding. So we not only showed protection, but also showed a reduction in shedding. And interestingly, as you can see here, we were able to identify antibodies which correlated with protection, and the total amount of IgG and IgA correlated with protection, as did antibody-dependent neutrophil phagocytosis. But something we're still not properly investigated is that we also found that if the vaccine-induced antibody-dependent NK cell activity, that was associated with increased susceptibility to typhoid. So an observation which I don't know whether will turn out to be real, but an interesting one to follow up on. So the exquisite ability to sample people in challenge studies means you can learn a lot more about the biology, and we've many more things that I don't have time to talk about today. But the critical point of the challenge model was it gave the World Health Organization confidence in the vaccine. And so they pre-qualified the vaccine as a result of the data, and there was then a policy recommendation that all children under the age of 15 in these high burden areas should be vaccinated to try and prevent the disease and reduce the spread of antibiotic resistance. Unfortunately, the Global Alliance for Vaccine then released $80 million to help countries start rolling out the vaccine. And this happened at the beginning of 2018. So countries began to apply for funding to start using the vaccine. But there was some reluctance still, because they're saying, okay, you've done it, you've got some evidence from a challenge model, but how do we actually implement this? And so we were funded by the Bill and Melinda Gates Foundation to go back to those populations where we had the burden data, to then go into the population and see whether the vaccine worked, using a randomized controlled trial where they either received the typhoid vaccine or a control. And what we found in these studies was that the vaccine provided 80% protection in the field, which then really has galvanized interest in rolling out of the vaccine. Unfortunately, the pandemic arrived at that moment, so things were slowed down a little bit. But despite that, in the last couple of years, about 60 million doses have been rolled out, including 7 million children in Nepal were vaccinated in 2022, and in Pakistan, they remarkably had vaccinated the year before about 1 million children every single day to try and cover the whole population of that. So these studies were able to support the rollout of typhoid vaccines, and now that has really accelerated, and we're seeing many more countries introducing typhoid vaccine.
It's working actually, sir.
Yeah, I could point to the screen, but to switch. Okay. Well, that's the pointer, right? That's the pointer. Yes, so 60 million doses rolled out over the last couple of years. So I think one of the nice things about this is the reminder that it's not just about the development of the vaccine. You have to build the whole program around the vaccine, build confidence for regulators, for policymakers, but also for governments. Because it's no good having a policymaker and a regulator saying it's a good idea, but governments have to spend the money. So they have to know that the vaccine that you're developing is going to have an impact in their population. And so having an idea about the burden of disease. And even in settings where everyone knows there's a burden of disease, the critical question is it enough to warrant vaccinating everyone? Can a government afford to vaccinate everyone? Will it buy enough economic benefit for the country to make it worthwhile doing that? And one of the real challenges that we've discovered in now starting to follow these children is that in those who are the youngest when they're vaccinated, who are the ones in grey here, over a 5-year period, we've now got follow-up of the children in the trials this is in Bangladesh, they run out of antibody very quickly. And so they become susceptible again as you get to this point where the antibody has fallen very rapidly. And I think it's interesting to note here that whatever age you are, this is the under 2s, 2 to 4 year olds and 5 to 15 year olds. At all ages, a month after you've been vaccinated, they make great immune responses to this vaccine. But then over time, the youngest age group lose their antibody much faster. And although I haven't put it on this slide, we've also looked at what happens to protection, and they, by this time, in Bangladesh, where there's a very high force of infection, they've lost their protection. So this tells you that they're going to need boosters in Bangladesh in the future. They've only just introduced the vaccine this year for the whole population, but they will need to boost. Other countries with a very low force of infection, where the dose that you're exposed to is lower, may well not need boosters quite as frequently or not as early, because they don't need so much antibody to defend them against a small dose, but you need more antibody to defend you against the high dose, which is what you get in Bangladesh, where the water is teeming with these bacteria. Okay, so this is now, those studies have just finished. This is 2019, and this is what the team looked like, having got huge experience from running many studies in the UK, lots of international studies. I've shown you a couple of them here. And then, of course, this happened. The first reports of a new virus emerging in Wuhan in China. And I like this slide, particularly from the New York Times, because it reports the first death from Wuhan, from the new coronavirus, and makes the point that the virus doesn't spread between people, which obviously proved to be completely incorrect. But it's also reassuring that the newspapers are always wrong, even today, but they were wrong on that one as well. And they've never retracted the article, though. And I think it's interesting just to reflect on the fact that on the 11th of January, which is when that slide, or at least that newspaper article was published, in Oxford we already knew the sequence of the virus. 11th of January. It had already been posted by Chinese scientists. It had been known by Chinese and Australian scientists for about 4 days by then. They knew the sequence. And they wanted to spend more time verifying that the virus that they'd isolated wasn't just some rare variant and that it was there consistently. But as events overtook them, they then made the sequence available on the 11th of January, and then it was used around the world for making vaccines at that point. So that's so early, before certainly I think probably anyone in this room knew that we were about to have a pandemic, and that it was already available. And it's interesting to reflect back to one of the most important pandemics ever in history, which is the Black Death. Arrived in England in 1348, having started spreading across Europe in 1347. And about half of the population died during the Black Death. So 50%, so let's say about half of the room was all dead. If we were in 1348. It didn't matter what age you were, half of the population went out. And at that time, no one had any idea it was an infection, let alone how it was transmitted. As it turns out, it almost certainly arrived, if we look at England, it came into Weymouth Harbour, which is a town on the south coast of England, and almost certainly came ashore in the fleas of rodents, of rats that were on the ship. But then it was spread person to person. And the reason why we think it spread person to person, it spread so rapidly, which doesn't happen with rats. And the mortality was very high. And the mortality is high when you have pneumonic plague, that is spread from aerosols from people, from person to person. So half the population died as a result of that. So we now know how it was spread. But can you imagine living in that population? People were frightened of their children when they became unwell. They didn't go out because they had no idea how this terrible disease was spread. And yet now in 2020s, we know the sequence. Within a few days. I think it's quite a remarkable difference, and the fear and the terror of the unknown compared with where we are today. So this is the Oxford vaccine, which I know you're very familiar here with viral vectors, but the vector we use is a chimpanzee adenovirus. Chimpanzee adenovirus because the pre-existing immune response, these antibody responses to chimpanzee viruses are much lower than for human adenoviruses, and the spike protein genes inserted into the virus so that it then, when it is used for vaccination, the spike protein is expressed. And I think one really important thing about the coronavirus pandemic is that we already knew exactly how to make coronavirus vaccines. We knew that if you took spike protein from SARS, which had caused an outbreak in 2002, or MERS, which caused an outbreak in 2012 and has had sporadic cases since then, that the spike protein in animals could be used as a highly protective antigen with almost whichever platform you use. So the actual research of what to do, how to make the vaccines in different platform technologies, inactivated vaccines, viral vectors, that was all done. And that took us 20 years of research on coronavirus, which of course we don't have for almost all of the other outbreak diseases that one might be worried about. But for this one, we had a lot of information already. And I think particularly worryingly here was that for SARS, mortality was about 11%. But some of the analysis for MERS suggested mortality, at least of those detected cases, was about 30%. So we're sort of in the territory of the Black Death. Not 50% of the room, but a third of the room dead, if we'd had a MERS-like infection that spread. And so government had already started investing in coronavirus vaccines in the UK from about 2015. And so my colleague in Oxford, Sarah Gilbert, had already run a trial of a MERS coronavirus vaccine, which was published a bit later than that, but the trial had already finished. We knew that with a MERS coronavirus vaccine, we got complete protection in non-human primates, and the immune responses in humans was pretty much identical to those non-human primates. It gives huge confidence that if there is a coronavirus pandemic from another coronavirus, you're going to have a protective vaccine. The only uncertainty really is in a human population, what level of protection you get. We already knew it would work, we just didn't know what level of protection. And the other question always is, can you manufacture at scale? We'd only done relatively small scale manufacturing. Of course, then we became very familiar with COVID. There were, I'm sure on your television screens as well as ours, lots of very severe cases in the hospitals. And the other challenge was that everyone was saying it's not possible to make a vaccine quickly, and you made that point in the introduction that it looked impossible. In fact, in the UK they were saying 2 to 5 years to develop a vaccine. And the reason actually for this long development is partly the R&D, which can take decades, but that's already done. We already knew how to make the vaccine. The process of manufacturing and clinical trials for most vaccines that we use routinely today takes 10 to 15 years. And if you unpick why that is, the largest question is the decision making between the steps in clinical development. First of all, it's getting into the clinic, getting manufacturing started and doing the phase 1. But you do the phase 1, you have a good result, then you have to go and find someone to fund the next phase of development, or if you're a company, you have to go and persuade senior management that you've got good results and they should invest in the next bit of development. And then you have to manufacture the next batches for the further development. And we find that if you want to manufacture a batch of vaccines, you may have to wait 18 months or 2 years before you can get into a manufacturing facility to make the vaccine. So these delays are not really because it takes a long time to develop vaccines. It's because we take a long time to develop vaccines. And then the last bit, which is here, the upscaling, often will take several years to work out what worked very well in the laboratory and in small-scale trials. How do you scale that up to millions or billions of doses? And that usually takes a very long time to complete. So the full development of the Oxford coronavirus vaccine starts here when the sequence arrives in January of 2020. Pre-GMP work and animal studies here, finally able to start manufacturing in March of 2020, and the vaccine had completed its manufacturing for phase 1, and all of the release testing for that for regulatory release to the trial by the 22nd of April. And so we then, the very next day, started vaccination and gave the first dose in the phase 1 trial, and actually did a very large phase 1 trial, as you can see here, with 1,000 volunteers in the phase 1, which normally you perhaps have 40 or 50. We had 1,000 in our phase 1 trial. And so that process, getting to that point, was fairly standard. It's what we do all the time with vaccines getting into phase 1 trials. But we had quite a lot of experience of what to do next, because within the team, and I put this up as one of the few photos there is of me actually doing any work in the laboratory, so just to persuade George, I do occasionally go in for photo opportunities. But we had worked on H5N1 in the outbreak in 2005, Ebola in 2014, and of course the swine flu outbreak in 2009. So lots of experience of working with regulators, working with the process of rapid response, which is another challenge of the pandemic, is what are the systems that you need to activate in order to be able to move very quickly. And the other thing which I think is quite unusual in a university in the setup in Oxford is there's lots of people working on different vaccines, and you saw a little bit of that on my slide, and actually that's just within our department. But across the university, there's people who work on very many different types of vaccine, and they're driven by their interest in the disease or the technology to develop vaccines. And I think one of the things that gave us the scale that you need to develop a vaccine in the pandemic very rapidly was that we had to build a completely different aeroplane, and we could bring people together who don't normally work in the same team, don't work together. We could bring them all together under one team to then work on development of the COVID-19 vaccine. And I think this is a really important bit of how do you have an always-on approach to being ready for a pandemic or an outbreak, is that you need to have the capabilities in peacetime to be doing stuff, which means that when the outbreak happens, you can make things come together. So that phase 1 trial demonstrated that there were good antibody responses. We'd originally been advised by the mathematical modelers that the pandemic would be so rapid that you would never have time to give a second dose. So we originally thought we would make a 1-dose vaccine and never not give the second dose, because their view was that everyone who was dead, everyone who was going to die would be dead by the time you got to a second dose. So just if one dose doesn't work, you've got no chance. Of course, social distancing and lockdowns proved them wrong. And we found that 2 doses gave better antibody responses. This is neutralizing antibody, and we saw good T-cell responses with the vaccine. So that allowed us to move on to the next phases. This is a newspaper article. So we vaccinated that first volunteer on a Thursday, the 23rd of April. And then on the Sunday, I got a phone call saying there's a fake news website which says that that first volunteer has died. And that was then being reported across the media all over the world, that the first volunteer in the trial had died. And of course, the volunteer knew she wasn't dead, so she wasn't too concerned. But her family didn't know, and nor did her colleagues, and nor did any of the other trial volunteers in our trial, or in fact any of the other trials going on around the world. And so we were forced to, within an hour of this fake news website going live, doing a proof of life interview, like you might do in a hostage situation, to show that actually this person was still alive. And the BBC did that for us, and it was then picked up globally by the media to show that it was a fake news website. But some of the anti-vaccine lobbyists said because she wasn't holding up a newspaper showing the date, that we could have filmed it before she died. Anyway, there you go. So that brought us to the phase 2 clinical trials, which were to look across ages, and this showed that individuals, even if they were relatively elderly, and these 3 lines are 3 different ages, 18 to 55, 56, 69, and the over 70s, they all had very similar immune responses, independent of what age they were. And I think this gave a lot of confidence that we would see good protection across all ages. But actually, as has been shown with all of the vaccines, the frail elderly did make poorer immune responses. And I think you have this healthy volunteer problem in clinical trials, that if you're 80, but you're able to get on your bicycle and cycle to a vaccine centre, you're a very healthy person who's physiologically much younger, and you have good immune responses. But the very elderly, frail individuals tend not to have such good immune responses. I think that's something we need to understand more. So as we got to the point of releasing the first results from the trials, this was in July of 2020, we had huge amounts of media interest in what we were doing in our clinical development. This was Russian fake news which was being spread, put to the Times all over the world, but focusing on countries which were introducing the Russian vaccine as well as the Oxford vaccine, and suggesting that because it was a chimpanzee adenovirus, that it would result in people developing chimpanzee appearances as a result. And I don't know, has anyone seen Planet of the Apes? Yeah. So the Planet of the Apes, I don't know what that is in Portuguese, but Planet of the Apes, they took those videos from Planet of the Apes, and they made some brilliant videos showing how people who got the vaccine turned into the footage from that movie.
In Brazil, they become Oliveira.
But seriously, at this point, the university was receiving 1,000 contacts from journalists per hour, because people were so interested in what was happening, and it became completely unworkable. And you can't control what people are saying, because you can't talk to all of those journalists and give them a sensible view. So they write their own story. And there was a point at which I felt this was all quite stressful, until you realise that there's no way you can respond to that, and you can't control the narrative, so you just do what you can do and try and be honest with it. But it's a bit stressful. And really, I think the key next bit in this story was the phase 3 trials and the partnership. And in fact, I was contacting the teams here in Brazil within a week of giving that first dose in the phase 1 trial, because we knew we had to do very large-scale clinical trials in order to be able to demonstrate the vaccine worked. And it was important to us that we had not only showed that it worked for the British, but that it worked whichever population you're in, different social circumstances, different ethnic groups. And so we had plans for research, for trials here in Brazil and in South Africa and also in Asia. And so you can see those are the three sites. We had a number of trial sites across the UK, across Brazil, and across South Africa. And by this time, AstraZeneca had come on board to agree to help with the upscaling and the distribution of the vaccine. And they ran trials in the US, in Russia, and also in Japan. And that's because some jurisdictions require trials done in their countries in order to get licensure. So we didn't just do the clinical trials in those countries. And I think perhaps really importantly was for our South Asian vaccination program, the partnership was with Serum Institute of India, the world's largest vaccine producer. And so AstraZeneca made a contract with them to produce the vaccine, but also to run trials in the South Asian region, which they did. And so when we come to this phase 3 trial, about 25,000 people now have taken part in the clinical trials. And I always think it's remarkable when you start these trials, and I'm sure you'll have had experience of this as well, you go and talk to the volunteers and you say, I don't know if this vaccine will work, I don't know if it's safe, but will you take part in the study anyway? And they do, and there are tens of thousands of people wanted to take part in the clinical trials. And when you think about all of the development that happened during the pandemic with tens of thousands of people with Moderna and Pfizer and the Chinese vaccines, it's the most incredible connection between research that's involved the public and industry and academia, and that I think we'll ever see in our lifetime, to have that global involvement in research to have such an impact. So the development then took about 300 days to get to the point where at the end of November we had the first results, the interim results, which we could then present to regulators for the emergency use authorization, which then happened in the UK with our regulator at the end of December of 2020. And then just a few days later, the first dose was given in the UK. And a number of other countries approved the vaccine, including Brazil, very rapidly after that first approval in the UK. And as you mentioned in the introduction, over 180 countries then approved the vaccine for use. But importantly, the European Medicines Agency had been given the job of being the reference agency for the World Health Organization. And so although they were a bit slower, they did a month later approve the vaccine, which allowed the World Health Organization to approve it for global use in low and middle income countries, so that then the first dose was shipped via COVAX. Now COVAX was the mechanism for distribution of the vaccine around the world in an equitable way of any vaccine that was provided to them. But none of the other producers gave doses to COVAX at this stage because they could make profits by giving their doses to, or selling them to high-income countries largely. And so up until the end of May of 2021, 90% of the doses came from Oxford. And of course, when you think about mortality in a pandemic, you have to vaccinate people before they're dead, and most people who are going to die died by the end of 2021. And so the importance of early equitable distribution is really emphasised when you look at the mortality curves for coronavirus. So I'm just going to make one other point about this, which is that the reason why the Oxford vaccine was more equitably distributed was entirely down to the negotiations of the university with AstraZeneca. And other companies had also been spoken with, but AstraZeneca agreed that they would make a deal with the university to distribute the vaccine not for profit. And the reason why that's so unusual is that for most companies didn't really want to make vaccines in the pandemic because it was very high risk. You put a lot of resources into development and build plants and do lots of manufacturing, but you can guarantee in a pandemic that you won't have much supply 2 years later because people don't need the vaccine anymore. And so companies don't like the financial risk that they have to invest in it. And so we didn't have any vaccine from Sanofi Pasteur, GSK, from Merck, because there was it was high risk. They did a little bit of work on vaccine, but none of them actually made a vaccine in time to be used in the pandemic. And AstraZeneca, we insisted in Oxford that it was not-for-profit, but AstraZeneca didn't hesitate to say it's the right thing for the public good, and that meant that the vaccine could be distributed widely. I'm not sure that, having seen the extraordinary profits that Pfizer and Moderna have made, that any company will do that in the future pandemics. We should pay that through money. And I think these were perhaps the highlights for us, was seeing this rollout of the vaccine to countries which had no access at all to any vaccines, including the Dalai Lama getting his dose, as you can see there. I want to just very briefly digress to just mention that one of the other things about collecting samples in these clinical trials, you can answer so many questions in large-scale trials with efficacy as the endpoint that you can't address if you work with industry, because they're never interested, but having control over this yourself as a developer, you can do so much more. This is just one example which was looking at what genes are associated with immune responses and with protection. And you can see here that we found that in this initial cohort that we were able to find, you can see in the Manhattan plot, an HLA antigen that was associated, and then when we did finer mapping, you can see that it was HLA-DQ and DR. And the first observation was that individuals who had this particular genotype had a reduced risk of breakthrough infection. So in all of us now who are immune, have been vaccinated or have had infection, there is always someone here who said, oh, I keep getting COVID. Well, there's probably good reasons why some people are getting more breakthrough infections than others, and it's likely related to immunity. And similarly, we were able to show that there were differences in immune responses depending on the genotype of the individuals in the trial. This is obviously relevant to that moment in history when everyone was naive and they were getting their first doses. But I think it's a great opportunity to try and delve a bit further, because you're in the clinical development space, into the associations. Briefly, just on variants, we talked a little bit about that this afternoon with some of the students. We know that neutralizing antibodies associated with protection against infection. That's very clear from the trials run in Oxford and in Moderna. But it is a bit more complicated when we look at more severe disease, and this is a hamster challenge model. And you can see here hamster lungs, and these hamsters were either, well, these hamsters were naive, they're exposed to coronavirus, so this is a hamster exposed to the alpha variant, and you can see the lungs are very badly damaged by the coronavirus infection. For those of you not familiar with hamster lungs, these look horrible. And you can see lots of inflammatory infiltrating the lungs, and this is virus staining in the lung tissue. And here with the beta variant, exactly the same picture, very bad lungs infiltrate and staining of the virus. But in vaccinated animals here, who made very good neutralizing antibody responses, they have complete protection. These are normal lungs, because this animal's been vaccinated, there's no inflammation, no virus. So the vaccine is fantastic at blocking infection from the alpha variant, very close to the ancestral variant of SARS-CoV-2. But if you vaccinate animals and look at neutralizing antibody against the beta variant, the animals don't make a neutralizing antibody against beta variant. So you might predict that the vaccine wouldn't protect them, but actually they had complete protection from the beta variant. Normal lungs, no inflammation, no virus that you can see there. And so that tells you that neutralizing antibody, whilst they might be very important for blocking infection, are not actually critical for preventing severe disease and death. And we think this is true in humans as well. So we don't know for certain which immune responses are important for severe disease, because in the clinical trials, the end point of the trials is mild infection. And so to find any correlate that's for really bad lung disease, hospitalization, death, is impossible in humans. We've not been able to do that. But we do see lots of different T cell responses, so maybe the T cell compartment is critical for prevention of severe disease. With viral vectors, you see much stronger T cell responses in the lung than you do with RNA vaccines. But there isn't an obvious difference in their ability to prevent severe disease and death. So if it is T cell responses, it's not something we know how to measure. Similarly, there are lots of antibody functions that we are aware of with COVID that are not neutralizing. So maybe it's some other antibody functions that are critical in the lung that are not around for neutralizing antibody. One other thing I just wanted to say about this is this animal, these animals, although they had no disease at all in the lung, they did still shed virus, whereas these animals had almost no shedding of the virus. And I think this is very much like we all experience, that humans get infected with variants, but we're no longer getting lung disease because we were immune from vaccines and from past infection. Anyway, so I don't think we've unpicked this completely. There's some evidence in one non-human primate study that T cells are important. And although we can measure all of these things, we don't actually know in humans which are critical for this component. One of the downsides of the viral vector vaccine was it was associated with this very severe side effect, very rarely, but of thrombosis and thrombocytopenia. And in the UK and in Europe, when this was first identified, countries had very different responses. Some just stopped using the vaccine completely, which of course then meant that there were many unvaccinated people because there was a shortage of supply, who then were at very severe risk of dying from coronavirus. But in the UK, the approach was to carry on vaccinating and to accept a very small risk of a severe side effect because you were preventing a lot of deaths from vaccination. And this balance between the risk of ending up in intensive care versus the very low risk of developing thrombosis and thrombocytopenia was quite well communicated to the public at the time. And I think the UK government did a good job of doing that and almost certainly saved many lives, particularly in older adults, and by continuing with the vaccine program until there was enough supply to switch to other vaccines. And I think this is a great slide to summarize the enormous impact of the coronavirus vaccines. Here's the first wave in the UK before any vaccines were available, the second wave, and then the first doses became available. We haven't since then seen any other waves of pandemic levels of coronavirus deaths because the vaccines work so amazingly well that it doesn't continue to happen. And when we look at deaths averted, you can see here, this is global data from the company Affinity, who show that between AstraZeneca and Pfizer, in 2021 alone, somewhere around 11 million deaths were prevented. But you do need all of these other vaccines contributing to have the somewhere around 20 million lives saved in 2021 in order to have the impact that the global program of vaccination has had. Just very briefly on this slide to highlight that my point I made earlier, that all of the vaccines, so that if you're on the right-hand side, it means you're preventing death and severe disease. All of the vaccines, CoronaVac, RNA vaccines, viral vector vaccines, all of them were extremely good at preventing severe disease. And lots of media saying the Chinese vaccines didn't work as well. Well, they weren't quite as good at preventing infection, but they were perfectly adequate in preventing severe disease. And as fortunate they were so widely available, I know particularly here in Brazil. So we've come a long way since 1348 to 2020. The science is very much better. I should say there's been lots of other pandemics other than plague and coronavirus that have helped educate us over the years. But it is important to remember that there are lots of obstacles to vaccine development. In the pandemic, there were 349 vaccines being developed, but only 8 have been approved by the World Health Organization. And as you saw on the previous slide, fewer of those widely used around the world. I think that shows you that there are a lot of challenges, even if you make a vaccine that looks good in the laboratory, to actually getting it all the way through to a point where it can be widely deployed. I think that's one of the challenges for the future, is to try and unpick why we didn't have more successes there. So there's lots of aspects here around vaccine development I've talked about that will allow us to move more rapidly in the future by understanding better about each of these stages of discovery and development that many people have learned during the course of the pandemic. We may need that because there's constant outbreaks in the news, and you've had yours just recently here in Brazil to remind us that there are pathogens out there that there's very little work on at the moment. And the work over the last 60 years, since we've had programs in many countries for immunisation, shows the huge impact that vaccines can have if they're used. So most of these diseases, which before 1960 were extremely common in all countries, high and in low and middle-income countries, are now much less common. But I think being here in Brazil with the recent dengue outbreak and the Oropouche outbreak reminds us that we are in a moment in history, particularly with climate change, which means that vector-borne diseases, and perhaps others as well, could spread more readily. So there's an interesting data on that plague pandemic in 1340 suggesting it was climate change which changed the territories of rodents, which triggered that beginning of spread of infected fleas that eventually came to Europe and spread around the world. So I think we should be slightly concerned about the potential for more outbreaks of things we know about, but maybe also things that we don't know about. We're at about 8 billion people on the planet at the moment. The next 30 or 40 years we'll get up to about 11 billion. And so that increases the risk of transmission, particularly as people move into habitats that animals live in. And I mean, in many of our countries, with the increased frailty that there is in the population, means that there'll be many more vulnerable individuals as we travel around. And so there are a number of pathogen lists of things to focus on. This is the Coalition for Epidemic Preparedness list. The previous one was the UK government. And just last week in Rio, the World Health Organization launched a new list of pathogens that we should be focusing on because of the global threats that there are from pandemics. We've got the technologies. We have a lot of new knowledge about how to plan trials to better respond in outbreaks. And the G7 group of wealthy countries have a new mission, a 100-day mission, to try to get vaccines and therapeutics to be deployed at scale within 100 days. So I think certainly successful development is possible, but it does require an always-on approach to having stuff happening in peacetime, which means that you can adapt the knowledge and abilities that you have when a pandemic happens. And although it seems a bit worrying to have this scale of threats that are out there, I do think the science we have today has got this, and that there is going to be a way to better manage this as long as we invest in the research like I've been done with coronaviruses over the next few years. I'll just end with an acknowledgement slide. Thank you.
Thank you so much, Andy. It was remarkable on this story. We are open for questions.
Well, I'd like to really congratulate and say how important was your work for the entire world. Here. I've seen people talking about this 100 days vaccine. And I think always I look at that because even for the COVID that was maybe 9 months, one of the, I think the whole thing was very fast, but one of the main things that was questionable was the phase 3 clinical trial for 3 months. Lucky that it worked, but it could be, then I don't see a way you can do a phase 3 clinical trial in a week.
Well, I think it's a really good point that phase 3 clinical trials for safety, you need about, at least in Europe, about 3,000 people in the trial, in North America about 5,000. So the numbers required to recruit for those numbers can be done in a week in a pandemic. So that bit is fine. For efficacy, the issue is that the way efficacy trials are run is the accumulation of cases in the trial. So it's not the sample size of the trial. If you've got a very common disease, you can run the trial with a very small number of people, and you just have to have, let's say, 100 cases, which is what we needed for coronavirus. So if you want to run the trials quicker, you just run bigger trials. So instead of doing 25 or 40,000, you do 100,000 or 150,000. And that is entirely achievable if you've got clinical trial sites that are functioning and working all the time, which we do have around the world. The problem was no one would pay for that. And I think that's, if you recognize the importance from a recent pandemic and you have that in your pandemic planning for the future, you just run a bigger trial. And they're no more difficult logistically, you just run a bigger trial.
But then I remember the beginning of the testing, there was everybody worrying about the adjuvant. Often things like...
Do you mean worrying about the enhanced disease?
No, non-specific protection effect of the adjuvant. Like,
well, but there's no adjuvant in any of the vaccines.
The vaccine not protected, but having a
it protects, but
trained
non-specific.
immunity.
Oh, I see, trained immunity.
Yeah.
Yeah.
Or,
But I don't care what the mechanism of immunity is. I'd rather not die.
well, but that will take very short time.
Yeah, but you do need an observation period afterwards. But if you let's say we did have a pandemic with 30% of the population dying, we need to roll out vaccines and gather information.
It's not a vaccine, it's a completely different concept.
If it's yeah. For coronavirus vaccines, we already knew about direct protection in animals. We also knew about the nature of the immune responses induced, and so I don't think there was really a concern about that. But I mean, all of the efforts to look at trained immunity, like the huge BCG vaccine trials, they did not show any impact of trained immunity on protection. So boosting innate immune responses for a temporary period may be a good thing anyway.
Right.
But we don't actually have evidence that was important for coronavirus.
There is an online question. Brenda Martins is asking, first and foremost, congratulations for your presentation. I am interested in your perspective on the strategic realignment of vaccine for management of pandemic diseases.
I'm not quite sure what the strategic realignment question means, but I think if it's about countries aligning between them so that there's not duplication, I'm a bit nervous about that, because you actually do want duplication because not everything works. So some countries, funders have said, well, the Americans are doing that, so we don't need to. But I think that's a very risky approach to take. What you need is probably multiple developers taking different approaches against the same diseases, because we don't yet know for many of them which will be successful. And success is a scientific one, it's a manufacturing one, which, as we discussed earlier, is often the biggest hurdle in development, to work out, first of all, how do you make something to a quality that can be put into humans, and how do you upscale it? It's the biggest hurdle in vaccine development. And then obviously the clinical trials.
Any other question?
Thank you for the great talk. Remind us what we've been through.
Yeah, sorry about in case that was too painful to go through it again.
It's very good to see how the vaccine changed the game, and that was great. But I would like to ask about the control infections. I know you guys going to discuss a lot about that. And you showed an example for the typhoid vaccine. And I would like to know how important for the COVID vaccine was this strategy. And second, to see how the population in England, how this kind of strategy is seen by
Okay, well, so I'm going to ask Daniela to answer the second question, but the first question, for COVID challenge, I think it's been a very interesting scientific process. Where it might have been really important is if these vaccines had all failed, and we needed to go back and try and work out what's going on immunologically, why the vaccine's not working, and perhaps start testing different types of constructs. As it turned out, it was perfectly possible for multiple developers to develop using traditional field efficacy trials. So I don't think it's been important in this pandemic, apart from some interesting scientific observations, but it might have been. And I think one of the things that we should be doing is having a plan that we prepare for challenge studies early in pandemics, even if we don't ever use them, so that if we do find we need to use them, that we're not then waiting for another year to persuade someone to manufacture the challenge agent and to set up the protocols. So yeah, I think this one wasn't a good example, but we will talk more about challenge models over the next few days.
I was doing an urgent peak, so can you please repeat the second part of the question?
The question was about what does the public think about, governments think about challenge studies?
Yeah, so in the UK particularly, yeah. So it's a very favorable view environment, both by regulators and ethics and the public particularly, which I think it shows the maturity of the country. Have done these studies for a number of years, from many different investigators and models, but also the very closely working relationship that there is between the investigators in trial sites and the public. And I think this was it's a very remarkable to see how in the UK that is very well done. People understand what they're doing and they're part, and they're very proud to be part of it. And it has been really important, as Andrew has mentioned, for some of the vaccines and how we actually allowed development to move much quicker, as well as understanding of disease. Yeah, I'm very excited about the next 2 days of that talk.
Yeah, just on this, when UK released, started recruiting for the COVID challenge, 15,000 Brazilians registered to be volunteer in the trial. So just
I didn't know that. That's a great figure.
Yeah.
The other thing that sort of follow up on Daniela's comments, when I went to the ethics committee in 2010, 2011, the typhoid challenge, when we were just setting up the model, I was quite nervous about going to talk to the committee about it. And I went in there, and there was this large group of people around the table, and they said, "We don't have any questions for you, but it's fine. Just carry on." And I said, "Well, I've got some questions for you." And so we discussed lots of the issues I was worried about, but they thought this is absolutely fine. So it's a quite remarkable experience.
just like Brazil. And about.
Thank you very much for the nice talk. Congratulations for this wonderful work. My question is, how do you see the future of the adenovirus vaccine platform? Since it has gone to real world problems with the side effects, etc. And that the other vaccines in this platform that Oxford is developed, such as the Beige vaccine.
So I think if there was an outbreak tomorrow of a severe disease with high fatality, it would be absolutely appropriate to use a viral vector vaccine. I would take one in that situation straight away. But if you're trying to develop vaccines for peacetime, where for the general population, most people are never going to be exposed to many of the pathogens we vaccinate for, then the risk-benefit needs to be adjusted. So you might choose a recombinant protein vaccine instead, because it would have a much lower risk, as long as it works, obviously, assuming they all work. You would look at the risk-benefit. But if you have no alternatives, as for many of these pathogens we don't at the moment, then you would, and there's an outbreak happening, then you would use a viral vector vaccine. But I think the regulatory position is rather like that. It's always looking at risk and benefit. In the UK, if we had a viral vector RSV vaccine, we wouldn't be giving that to pregnant women, because the risk benefit is not in favour of doing that in the UK, where there's a very low risk of mortality in the infant. But if there was a very high mortality from a different disease, maybe a Lassa fever outbreak with a high mortality, you might still deploy viral vector vaccine if there's no alternative. And of course, in outbreaks, there's always a supply problem. So currently, funders are still funding in the platform, because if tomorrow we have another pandemic and we need to make vaccines at scale, as you saw, the only vaccines made at scale were viral vectors and RNA vaccines. So we ought to vaccinate the world against the threat. We have to have viral vectors at this moment in history.
In your talk, you mentioned about dealing with fake news, which is like a very important thing, probably all over now. Any advice to bring better education to the general population and to prevent fake news or spreading?
Yeah, I mean, I think there's a couple of things which you can learn from the business world, because they're always involved in scandals in the business world. But what they don't do is go repeatedly into the media and deny the scandals, and well, maybe they do in Brazil, but I think the advice is not to do that, because as soon as you go and start speaking about the issue, you amplify the negative. And so with the problem with some of the misinformation is if you spend all your time countering the misinformation, you're telling the public that there's two sides to the story, and you're amplifying the misinformation by doing it. So I think the current view, and I don't think any country in the world does this well, but the current view from psychologists is you have to just constantly push positive messages. And if we're all confident that vaccines are the right thing to do and we have a good understanding of them, then we find that the whole view of the public changes. And we have other, at least in my experience, other public health messages which have worked. I remember in the UK when mandatory seatbelts were brought in, and there were lots of people saying, well, I'll be trapped in my car in an accident and I'll burn to death, I don't want to wear a seatbelt. But now, certainly in the UK, if I get into the car and someone doesn't have their seatbelt on, I won't drive off until they put it on. And in fact, then the car will start making a noise to tell me they don't have the seatbelt on. And it's become normal because the messaging has been extremely good about seatbelts and why we need them, and there's a law which probably helps. And then the other one was the smoking ban from nearly 20 years ago now in the UK. There was lots of pressure against that from pubs, from the tobacco lobby. But actually now if someone was to smoke in a restaurant in an enclosed space, everyone around them would tell them to stop. And so you need to be in a position where the messages are so strong to the public around you that vaccines are the right thing to do, and that if your child isn't vaccinated, other people will tell you it's no good you starting to tell people because you're obviously being paid by Bill Gates to spread misinformation.
Yeah. Any other question? Okay, Andy, thank you so much. It was fantastic.
Thank you.